All right. So good morning, everyone. I don't know if there are people online or not, but so today we're going to start lecture 16. Are there questions before I start? This is going to be the last lecture from part 2 of the course, which is about quantum dynamics. And yeah, any questions? If there are questions that come up as we go along, so just ask. I've prepared more material that I will probably have time to present. So the leftovers of it, it's all on the slides. I recommend that you look at them later. It's not part of the course, but it's a logical continuation of what we're gonna discuss. All right. So in particular, Feynman path integrals. I'll just set up the story. Feynman path integrals are extremely convenient calculationally, and it just gives you a very, very useful way of thinking about quantum mechanics. All right. I absolutely recommend that you guys at least read over it. Okay. So what did we talk about last time? The WKB approximation. I did not look up what WKB stands for, the names again. Nobody cares. This is recorded, sorry. It's a technique to obtain approximate solutions to time-independent Schrodinger equations in one dimensions. So last time when I said this, I didn't say one dimensions. There's a reason for that, because like higher dimensional systems often using symmetry or something, you could turn it into one dimensional. For example, you could talk about radial component of a higher dimensional problem if could be effectively a one dimensional, and then you might be able to use WKB as we do actually. But the example we're going to be discussing is just one dimensional. So what was the idea? I'm going to present the idea from a different perspective. So everything I said will match whatever I had said before, but it's a different perspective. Perhaps a less math heavy, more word heavy presentation. So the idea is that you have a particle with energy E moving through a region with some potential. The property of this potential is that the potential in that region is almost flat. It's almost constant, right? So the particle is moving. Let's say the particle is moving in this room, and the potential is defined everywhere in the universe, and the rate of variation of the potential in this room is very, very slow, so that you could approximately think of it as constant in this room, right? Then it's easy to solve the Schrodinger equation locally, right? It's just a constant potential, right? What is the solution? So we have IH bar dt of psi, right, is Hamiltonian, right, which is p squared over 2m. Oh, actually, no, sorry. I want to solve the time-independent equation. So it would be p squared over 2m, right, plus v of x, which I'm going to take to be a constant. So v psi is e psi. So what's the solution to this? It's just plain wave, right? The solution to this is precisely just a plain wave where k, the momentum mode, square root 2m e minus v. Is that clear? Right? This is just a plain wave solution. So what is the idea? The idea is if the potential is varying very slowly in the universe, split the universe into boxes. This room, the next room, room next door, and just so on and so forth. You solve the equation, approximate the equation locally using one of these waves. And then you say, as you go from this room to the next room, the variable k changes from this room to the next room, right? So it's an approximation where you locally solve it using a wave equation, local equation, and just patch the solution and go along, right? What is the idea? You just promote this k to, well, I called it p of x, right? To something x dependent, where x dependence is in v, right? Is that clear? Right? So you think of this as a solution here. Potential is fixed, so it's just some wave, right? The wavelength is set by the potential, This is the wavelength, lambda, right? This is the wavelength, it's inverse wavelength. As you go to the next room, it's still this oscillatory wave, but the wavelength has changed. So the wavelength becomes potential dependent. It's an approximation method. I motivated this through the connection with classical physics, but this is an alternative way of thinking about the same thing. You realize that these set of words are not rigorous. When I say potential is almost constant, you have to ask with respect to what, right? We clarified that mathematically and physically last time, but now I'm just giving you an intuitive feel for it. All right. And the idea is that v of x is not constant, but varies slowly in comparison to lambda. What is lambda? 2 pi over k, right? This is a de Broglie, I can never pronounce this name, even though I speak French. De Broglie wavelength associated to the particle. All right. Of course, this solution applies literally in the classical region where E is larger, energy is larger than the potential V of X, right? So we saw how it works. This is the Schrodinger equation, time independent Schrodinger equation, right? So what we're gonna do is that we're gonna take V of X to the right side, right? Then write it as an operator P squared acting on psi. P squared over minus P squared over H bar acting on psi. Well, actually, H bar is coming from here. I think it's H bar 2. Okay. Good. All right. So just to connect it with what the way I presented things last time what we're saying was that psi of x, you take the absolute value of it out, right? I wrote it as square root rho. This is rho. This is the only rho that there is in this lecture. There won't be any other rhos. And then the phase I wrote as e to the power of I s of x over h bar, right? Well, there was time dependence, but these are stationary solutions. So we separated s of x into w of x minus e of et, all of that. You recall that, right? So I'm suppressing all that notation here just to make a connection with what we said before, right? And then the final result of all that long song and dance was that we found the psi of x, if you set the phase to 0, the oscillatory phase, time dependence, if you just discard the time dependence, is going to be a constant over square root of p of x, that p of x we just defined, e to the power of plus minus I over h bar integral 0 to x of p of x prime d of x prime, right? This was the solution. So what we're going to do, I'm going to pause here and answer questions, but what we're going to do to build intuition about this is to solve two crucial examples, two examples that are very important. And I will not go through the example that I motivated last time. I started with last time, which was a potential with 3 regions, 1, 2, 3. Well, these are of the same nature, but that calculation will take the whole lecture. So you will see in these two examples how it works. And I might actually include it as a homework, but that calculation is just a typical calculation that appears in quantum mechanics. But these are two crucial points, two crucial examples. Any questions about what WKB approximation is? I'm not sure if the online people can ask questions or whether we hear them. Do not say this loud. Yeah.
What people say to be counter like nearly constant potential? Because like I know we deal with harmonic oscillators a lot in physics.
Anyone?
I know you say cosmology.
Yeah. No, but like simpler examples. think of a setup. Let's say you're in the lab and you have designed a potential. Say it's like some sort of a laser trap for atoms, right? You know the form of the potential you design. There's some sort of magnetic field or whatever that you've designed, and you know the scale of it. So if you want to see whether, now you want to trap a particle in there. You want to see in what regime is WKB would be a good approximation. How would you do it? So you know the form of the potential and how fast it varies. What should you compare it to?
The energy, like the wavelength.
The wavelength, the early wavelength of the particle, right? Which is set by the energy, by the energy in a sense. But it's pretty straightforward. Actually, even if you want to trap the particle at rest, mass of it really the only thing that matters, right? So every particle to an electron it could associate a wavelength. This is what the whole idea of quantum mechanics was, right? To all sorts of particles, you could associate a wavelength, and if the wavelength is much smaller than v of x, it's a justified approximation. There are subtleties that we went over, but yeah. For instance, let me give an example. The lighter the particle, the larger the wavelength, its associated wavelength, the harder it is to use the WKB approximation, right? Another way of saying the same thing. If a particle is very, very light, it will go through anything. Like neutrinos, they're super light. It's hard to stop them, right? It basically goes through all potentials. But anyway, sorry, I'm going on tangents. All right, so examples. Any other questions? So the simplest example we could discuss is an infinite well that you know how to solve in quantum mechanics exactly if so it's infinite to the left for negative x, it's infinite to the right of a. You know how to solve it if it were constant in between the two, right? It's just like cosine and sines. But here we're going to take it to be an arbitrary thing, right? This would be literally like a really, really good trap, like laser trap for an atom. You know that you have trapped your atom in some distance. The atom cannot be outside of your sample, right? But then you engineer some potential here. So this is what we're going to approximate solution to this equation. Inside the well, in here, energy is going to be larger than V of x, right? Of course, otherwise there won't be any solutions. So we have, I don't know why sometimes it erases some of the letters. So we have the WKB approximation, which is this thing. So you see, there are two solutions. There is a plus sign, there is a minus sign, right? This is a differential. We're solving the Schrodinger equation. It's a second order differential equation. There are always two independent solutions, right? And the way you fix them is using boundary conditions, boundary value problem. Is that good? What are your boundary conditions? The wave function will have to vanish at this point. Will have to vanish at this point. Why is that? It's an even potential. There's no way the particle could leak out to anything else. There's no way for it to tunnel to anything else. If this were not, well, okay, there are a whole bunch of things. Well, we will actually, I'll actually comment on this. All right, so you could rewrite these two exponents as cosine and sine, sine and cosine. Is that clear to everyone? Right? So there will be two constants that are written as C1 and C2. All right, and the phi of x is just some short expression I'm using for this interval, this exponent. At x equals 0, psi has to be 0. So phi of 0 is 0, and the way to arrange for that is to set C2 equals 0. Good? At x equal a, phi of a has to be 0, and the way to arrange for it is to set phi of a equal n pi, right? Because sine is periodic with period pi. All right, so these are boundary conditions. As a result, you get this, and then that's it. That's basically your solution. As a result, you find that you get this quantization condition. Integral is 0 to a of p of x d of x is n pi h bar, right? So this is your solution, your whole solution, because you know what p of x is. It's just this thing, right? Any questions? So we solved it. It's very straightforward. Of course, if the approximation is valid. So this is a very simple example, but there is a point to it. The next example, so this is a setup where we're solving, if you recall the example, the structure I was describing had three regions: region 1, region 2, region 3. Region 1 and 3 were classically forbidden. Region 2 was classically possible, and what we just solved for is region 2. We zoomed in on region 2 by making the potential infinite to kill the region 1 and 3. Right? That's what we did. Now I'm going to do the opposite. I'm going to focus on an example that basically focuses on region 1 and 2. All right? So here's what it is. It's tunneling problem. You have a potential here. Here, to the left of 0, potential is 0. To the right of A, potential is a 0. And in between, there's a barrier, right? And we're gonna pick the energy of the solution so that the particle does not have enough energy to classically go through this barrier. If the energy of the particle was high up here, it would just classically go through this. But we're interested in a phenomenon where is about me punching this chalkboard and my hand coming out on the other side, right? That's what it is. This is the potential, and this is a particle that's moving, and there's a tunneling out where classically forbidden is this going through, right? All right. So here the point is to highlight an interesting structure. What are the solutions of the Schrodinger equation on region 1 and 3? No, region 1 and 3, plane waves, because the potential is 0, right? So now I have to set my boundary conditions. Previously, I had a trapped particle, so the boundary conditions are obvious. Here, no rule tells me, there's no principle that tells me what is it, the wave function here far away at the infinity at left, what's the wave function far at right, right? So there is a spectrum. There's, if you recall, like quantum mechanically, we said that spectrum could be continuous. I can have a particle of my favorite energy propagate in flat space, right? So here, I'm gonna set up the problem as a scattering problem. I have a particle coming from the left. I'm punching this wall from this direction, right? There's an amplitude for for it to bounce back, and there's an amplitude for this to go through. So quantum mechanically, what I'm solving this way, right? If this is to be a solution, there is the piece of the wave that's going this way, and then simultaneously there is the amplitude for it to come back. So I have to add them, right? So A is the incoming and B is the reflection. So the solution to the Schrodinger equation on this side is going to be A e to the power of I kx. K is chosen, so that's moving to the right, plus B e minus I kx. The minus sign means that it's moving back to the left, right? That's just a bounce. Yeah.
I don't understand how you're like describing this time-dependent process using time-independent.
Yeah, very good. Does anyone know the answer to that question? How did we deal with the time dependence? The time dependence of it is very trivial. These are stationary states. There's just a phase. It's e to the power of I e t, and the dispersion energy as a function of k, we know exactly what it is because it's plane wave. So it is true that I should be keeping track of it, but once you plug it in the differential equation, everything drops out. These are still stationary solutions. There are phases, of course, but the phase part is trivial. Stationary doesn't mean time independent. The expectation values are time independent. The wave function evolves with a phase, which means that once you calculate the expectation value, the phase is cancelled. That's a good question. Yeah.
It's sort of like a steady state.
Yeah, these are studies.
It's like, but
I think the term is stationary. There's a subtle distinction between the two that physicists make, just the words.
and it's mainly because like the potentials are just
Flat.
static.
Yeah. The potential is like, when I say
There's no
flat,
time
it means constant.
Yeah, there's no time dependence on the.
Oh, absolutely. The moment you have a time dependence, it's a mess. Actually, no, I'm not gonna go on tangents. There's a beautiful story of time. Like, yeah. All right. Philosophically, it's very interesting to think about time-dependent potentials. But anyway. All right. So in region 1, the solution is this. Region 3, right? It's just a wave that makes it out, right? There's nothing coming in on this side. What I'm actually doing is I should be taking A and B, F, and I don't know, something else, but I'm picking boundary conditions at infinity that kills that. And that corresponds to scattering problem from the left, right? That's just what I'm doing. It's solving a differential equation. Now the question is, what is it in the middle? Here's something very subtle. So we said this is classically forbidden region, right? And what we proposed as a solution for it was e to the power of minus 1 over h bar this form and e to the power of 1 over h bar this form. What are these? These are basically plugging in for, let me just scroll up all the way. So when it's classically forbidden, v of x is larger than e under square root, you have a minus sign. You take the minus sign out, that's an I. That I in plus minus I will give you an exponentially growing and exponentially decaying solution, right? That's the origin of it. Here are the two terms, exponentially growing and exponentially decaying. So I'm going to simplify your life. If this barrier is very wide or very tall, this exponentially growing coefficient has to be very, very small. I just argued physically. I have to argue by using differential equations, but I'm not going to do that to save time, right? If it's very, very wide or it's very, very tall, right? The amplitude for the wave function to grow, the term that has the growing piece will have to vanish. Think about why. Okay, think about why. What is the math? So this is a physics intuition. What is the math? How is it reflected in mathematics? Think about that. Okay. So here's I made the statement. Think about why this D I can ignore. Right. For example, this chalkboard. This is like the potential. The width of it might not be much, right? Because I don't know how thick the wall is, but the height of it is big. The potential is very large. Like as I punch this, I need a lot more kinetic energy to destroy the wall, right? Classically. All right. So we're going to make the approximation that D is not there, which means that in between what happens from here to here, the solution is an exponentially decaying thing. Something like this. So what does the solution look like? Let me just plot it again. Well, actually, let me plot it on the board. So the solution looks like this. So this is region 2. Here, there's a wave that's coming. Oh, sorry. I'm plotting the phase. No. What am I plotting? I don't want to plot this. I'm plotting the exponent. So what is the wave function? The wave function is proportional to e to the power of I phi of x. In this region, there's some wave like this. It's like some wave like this. And in this and then it will have to decay very, very fast. I understand that this is no longer phase. I'm still plotting phi of x, right? And then on this side, it will do the equations. So roughly speaking, this is what it is. All right. So now you immediately learn that the amplitude of the oscillations is F on this side. The amplitude of the incoming wave is A. So how much A? So comparing A and F is about how far exponential has brought you down, right? So f over a, whoops. F over a would be precisely this amount of potential, this exponent, right? How much is dropping. The tunneling amplitude, tunneling is quantum tunneling. The violation of classical physics is basically f squared over a squared. Why? Because those are the probabilities, right? So we can write it as e to the power of minus 2 gamma, and this is gamma, right? So the wider the wall, the potential, and the higher the potential, the more unlikely, unlikely it is for me to tunnel through. If the potential is not very tall or not very wide, there's a higher probability for tunneling. Yeah.
So can we say it's not a unitary process like the
no, it is a unitary process because there is a reflection. I'm ignoring the reflection. Actually, that's a very good question. That means that the amplitude for that you could check unitarity explicitly. Yeah. Amplitude for going through and reflection should add up to 1. The probability should add up. You could check unitarity. But if you ignore this bit, it's not. So here's a beautiful, what you just said is a beautiful statement. Enrico Fermi, back in his time, first part of 20th century, speculated a particle called neutrino, because he was Italian and he wanted to call it neutron, but little neutron, so neutrino, right? What was the speculation based on? It was a scattering process that had some missing piece. If you looked at the amplitudes for ingoing and outgoing, the outgoing things were not adding up to 1. So he speculated unitarity must be there. There must be a particle that is escaping and we're not seeing it. And he called it neutrino. It took so many years later for it to be discovered. You're not going to, we're actually using this principle as a way of discovering particles. It's wacky if you want to consider violation of conservation of probabilities, right? Unitarity, I mean, okay, I'm not going to talk about this, but the whole black hole information loss paradox is all about this. All right, good. So these are the 2 examples I wanted to go over quickly. Now, the example I was discussing where the potential was there was some potential in the middle and then something out there, right? This was the last time I was quickly going through this and I had very, very high hopes for quickly arguing for what to expect. I think that was a little bit naive. The potential I was describing was something like this. I don't know, something here, and then going up there. The way you solve this is first, in region 1, a little bit away from this guy, you solve it by plane wave, right? And this is going to be decaying potential, a decaying wave function. Why is that? That's pretty clear, right? This is forbidden. Whatever energy it has, this keeps going up, so it's definitely forbidden. So if I don't have chalk, but like if I were plotting the solution, it will look like this. It will be decaying, exponentially decaying. In the middle is in region 2, so I'm intentionally drawing it a little bit away from region 1 because I said exactly at this point, this is where the energy meets, right? My approximation breaks down for sure, right? Similarly, I have some sort of decaying thing here. In the middle, I have some oscillatory decay, right? Now, when the approximation, so I also have to draw it a little bit away from it. So what happens to the oscillatory behavior at this point? It goes crazy, right? The oscillations, my approximation breaks down, but what it's actually saying is that the exponent is growing ridiculously. It's just doing crazy oscillations. So what we usually do is we truncate the solution here and here, a little bit away from them, and then we solve this piece of the differential equation and by expanding v of x linear. It turns out that the solution to those are airy functions, so we haven't seen them. It's some differential equation method. It's nothing really fancy. It's some airy functions. I can give you some intuition. Everywhere in physics, you want to patch an oscillatory behavior to an exponentially decaying behavior, airy function is going to be your friend, right? So basically that's how you patch the solutions and how you push through. But similar, the punchline, which I did not reproduce, but I just said it, is that in all of these problems, where is it? There is a quantization condition like this. The phase as it oscillates from here to here ends up being either like an integer times pi or integer plus half times pi. It doesn't get worse than that. Integer plus half times pi is really the quantization condition. All right, so this is as much as I wanted to say about WKB. Are there any questions? Yeah.
So, solution breaks down like an intermediate.
Mhm.
Why is it breaking down?
Oh, let's see that. Let's see that. So what happens at that point?
Like you're still in above the potential.
Look at this. Look at this. Right? E becomes equal to Vx at that point. Right? Because when E is larger than V of x, you're in the classically allowed region 2. In 1 and 3, E is less than V of x, so it's classically forbidden. At those points, this becomes 0. What was this? In the 2-region solution, this was the phase, the oscillatory phase that goes to 0. Right? And if you look at what was our approximation? Our approximation was that this had to be, well, sorry, no. It was the fact that well, I have to write the whole thing on the board again. The approximation breaks down at this point. Sorry, is that good? So the phase one sickness of it is that the phase goes to 0.
Yeah, is it like right at the zero crossing?
Yeah, the exact point here. Yes, at that exact point, that
That's
was
not like a broader region.
yeah. So you make this a little bit fatter. You solve it a little bit here, and then there's an interpolating area function. This is for those of you guys. This is crucial for those of you guys who end up doing any calculations in AMO physics. This is going to be a lot of this type of calculations. Good. Yeah.
So if there's like a region where WKB breaks down because the potential varies too fast or something like that, obviously that'll like throw off sort of the solution in that region.
Yeah.
But is that sort of like a local thing? Does it, damage solutions that are far away?
Very, very good question. Yes. Think about the approximation logic. It was splitting the universe into boxes. If within this box, your potential is almost constant, your solution is okay here. Now you just have to patch them, right? So there will be one of the boxes where the approximation breaks down, and you have to do something. You have to try to solve your equation separately at that point, the way we do here with the area functions. You just expand the potential to a linear order and you solve that, and there will be an interpolating function. We're physicists, right? We're approximating a global differential equation using local solutions. This is really not kosher. Mathematicians do not like this, but some differential equations are nice enough that you could do this. There's a lot of physics and math that goes into this, but yeah. Yeah, around this one. Taylor expanded, yes. Well, it depends how accurately you want to reproduce your solution. If you just want a solution that patches them, expand to a linear order and you'll find area functions. If you expand to the next order, what you're doing is that, so area function will tell you that, well, the level of, you're approximating the wave function, right? The level, how literally can you take it over here? Well, your approximation breaks down. How does it break down? You have to go to previous lecture to see exactly that. The previous lecture could turn into a quantification of your error bars. There's a whole mathematics behind that, right? But if you go to the next order, you could trust that a little bit more. One more comment I'll make, we'll come back to this later. You've seen this in quantum mechanics, previous quantum mechanics courses, but I want to absolutely make it the approximation. I said Taylor expanded. What if your potential doesn't have Taylor expansion? Like, give me an example of a potential that doesn't have Taylor expansion. Yeah, like discontinuous. It's something here and then jumps up here, right? If the potential is well, it doesn't even have to be discontinuous. It could be like this. This doesn't have a Taylor expansion, right? Because the left derivative and the right derivative don't match. What do you do in those points? If you're a mathematician, you go and take a course in functional analysis. If you're a physicist, you put the Dirac delta function, right? Those are Euler's derivatives. I'll make that comment later. You've seen this before, hopefully, yes.
Compared to like a numerical solver.
What?
A
Numerical solver. Okay.
You just put this in.
100%.
And then, like, how did they match up? Like, why not just put it all into?
Sorry. You're suggesting putting this inside a numerical solver.
Yeah.
Compared to what you would do if you split it into pieces and do it. Well, if you put it in a numerical solver, depends. Somebody wrote that numerical solver code. If they were really, really smart, one part of the code would be, at first, you give it a potential, it does an analysis of where this potential is almost constant. And it splits it into regions and patches it. There's no magic to numerical solvers, right? These are all approximation methods. But I can tell you that no numerical solver would do WKB, guess WKB for you. It might be just like, it's actually I shouldn't say that. I don't know what the state of the art with numerical solvers are. But like, there's no magic to it, right? Somebody has done, numerical solver means that somebody has done this calculation for you already and coded it. Good. All right. Any other questions before I start talking about the propagator? So in the remainder of this lecture, I know it's a short amount of time, but what we're gonna do is I'm gonna build towards a notion of propagator that goes back to the earlier lectures and becomes conceptually important. It leads to another way of viewing quantum mechanics as path intervals. Okay, I'll probably have to use the word. So we're changing gears a little bit. What I want you to remember is lecture 1. We talked about 2 experiments, right? One experiment was this Stern-Gerlach thing. And the other experiment was the double slit. I think I was drawing it from the other way around. But the question was, where you have a particle, does it go through this hole or does it go through this hole? And then we found that if we don't observe it, there is an amplitude for it to go through this hole, and there's an amplitude for it to go through this hole. Right? So you are adding a phase here and a phase here. What we're going to do in this lecture is, the remainder of the lecture, I'm going to give you an analogy that could be made precise, and this is the genius of Feynman. He did this as a graduate student in Princeton, based on a footnote he read in a paper by Dirac, right? So here's the analogy. This is his thinking. He says, so the particle going here, we saw that in quantum mechanics, a lot of things are controlled by phase. So he said, the phase, if it's like, if I can approximate things with like this, these oscillatory things, it's like a clock, right? So somebody's walking along this path and their clock is just running. But this is just phase, right? So they said, okay, you have a clock here, it keeps running. And then there's a guy who walks along this and their clock keeps running. And then when I get there, I have to add up the legs of their watches like as vectors. If they're opposite, they will cancel, right? They might interfere constructively or not. Then he said, okay, so this is an experiment. What I'm gonna do is I'm gonna build this up with another one and another one and another one. So now this guy can come here, go through this path. It could do, I wish I had color, could do this path. So the amplitude to go from here to here becomes something that like this. You take an arbitrary path here, an arbitrary path here, an arbitrary path here, an arbitrary path here. And to each of these paths, you have to do the calculation of what happens to the guy's clock. Right? Where do they end up here? Where does the clock? The clock goes around, that's 2 clock, right? Where does it end up here? Where does it end up here? And you have to add up all of these over all possible paths. Because he's imagining a 4-slit experiment here, 4-slit experiment here, but then a continuous number of slit experiments everywhere along the way. So the weird part is, well, we're gonna talk about this, that what he defined, this is not an integral, this is a path integral. You're integrating over the space of all paths. And what he did was he said, I'm gonna reproduce quantum mechanics by doing these integrals. First of all, it's really wacky to think you can do these integrals, but it turns out you can. If you're Feynman, right? And of course, he pushed a whole bunch of infinities under Dirac, and we'll also do the same, but if you continue in theoretical physics, fast forward like a couple of decades, we learned that those infinities, why he could push under Dirac, and what's the physics of that. So that came back, we learned a lot about it, right? So this is the principle. We're going to reproduce quantum mechanics by doing these path integrals, right? Good. I know it's just a half of a lecture, but what I'm going to first do is to introduce the notion of propagator. Okay, so there are a couple of manipulations. They might look innocent looking, but they're somewhat deep. All right, so let's go through this. And I'm going to do them on the board if there are questions. Any questions about the philosophy? Yeah.
The clock comes into play because you want to wait paths that take less time higher, or
say it again.
the clocks come into play because you want to wait paths that take less time higher, or
No. We're just saying that, remember the wave function? We said there's a piece that is here, and then there's an exponent. He said, I'm going to focus on this piece, just the phases, right? And then there is a part here, but you will deal with it, and you can actually, right? He said that this is the clock, right? This is an oscillator behavior. He said, I'm going to focus only on this action. And I'm going to associate, well, to each action, to each path, there is a value of the action, right? There is, in this business, there is no classical physics to be found. We're going to see how classical physics comes about, right? When Feynman was doing this, he had no idea. I don't know. Maybe he could have guessed from day one, but it's just insane to think he could guess where classical physics comes. And to think of the fact that a graduate student in Princeton did this based on a footnote, it's just mind-blowing. But anyway, those were special times. Good. Any questions? All right. There's a, yeah. This kind of physics can only come out of, anyways, I'm not gonna make it funny. Anyway, all right. So here's a time evolution of a cat, right? So I'm gonna imagine a particle propagating in space. Initial state is ket alpha at time t0. We saw that the time evolution, if Hamiltonian is time independent, could be integrated this way. And this is the state ket at time t. Everybody's with me? All right. So we're going to be discussing the wave function at different times in position basis. Good. That is psi of x double prime of t. That is the following overlap. Good. All right. First thing, I'm going to put a resolution of identity for energy eigenkets in the middle. Why do I do that? So that I can, the action of this guy on the energy eigenket from the left gives me a phase, and I can bring the phase out. All right. Now, what is this? This is the energy eigenket A prime in position eigenbasis. right? We're gonna keep this term as is, and I'm gonna write it as u of a prime double x prime. That's what we were calling it before, but that's just this term. The phase is the phase. I'm gonna put it here. I'm gonna take this term, put it out here because I'm gonna massage this further. Notice that this is all the initial data. There's no time dependence in this piece. These are just coefficients of the initial wave function in energy eigenbasis. What I'm gonna do is I'm gonna insert a resolution of identity in position eigenbasis here. What do I get? Well, I have an integral over x because this is a resolution of identity of x. I'm gonna bring the integral out here. This term is the position wave function of energy eigen state A prime star, right? I've taken the complex conjugate of it. This term is the initial wave function in the x position basis. Good. So what did I accomplish? I wrote the energy, I wrote this wave function at time x, at time t in position eigenbasis as something acting on the wave function at time t0 in position. So what did I do? Think of this example. At time t naught, I measured my particle. It was here, right? At x prime. And then we're calculating the amplitude for that to end up at some double x prime here. This whole thing we are doing is that path integral that Feynman wanted to calculate. It's the amplitude for the particle to go from here to here. Right? This is the kernel. This is called a propagator. The propagator is the amplitude. We write it as k of x double prime t, x prime t naught. It's the amplitude to go from position x prime at time t naught to the position x double prime at time t. Good? And you know the form of it. It's basically this. This is the propagator. Let's start this for a little bit and see if there are any questions. So I basically managed to write down the time evolution of states, all in terms of some differential over something that acts in the position eigenbasis. I just wrote everything in terms of the wave functions. This is called propagator. By the way, if you're a mathematician, this is all familiar to you because even if you have not, like this is a typical method to solve differential equations. But for physicists, every term has a meaning. Mathematicians know a lot, but they don't know what they know. All right. I wish there was a button I could press so that something not recorded and could go back online. All right. So what is it? This, sorry? I can? That is, okay, that would be super awkward. All right. Maybe I should not put these videos on YouTube. I can put them on YouTube and just make them accessible only to you guys. That's also an option. All right. Here's a propagator, and I've just put together all these terms, right? And I wrote what these terms were in terms of, like brackets. This is the propagator, and I just told you what it is. And written, I can write it this way, right? This is really nothing but evolution operator in position eigenbasis. Matrix elements of the evolution operator in position eigenbasis. That's what the propagator is. I just described it in words. This is the time evolution operator from t naught to t in position eigenbasis. Good. Notice that there is this phase thing. This is the inspiration of Feynman. There's a phase, and we're going to keep track of that phase. Good. It's actually kind of interesting. There's a book by Dirac from quantum mechanics. It's very thin. It's like really thin. maybe less than 100 pages or something like that. If you read that book, yeah, I recommend if you have free time, just read the book. It's just kind of crazy. Yeah, he basically describes a lot of things in this terminology. So if you're Feynman, yeah, now in retrospect, the leap, it doesn't seem big, but at the time it was big, right? Anyway, so what are the properties of the propagator? For time t larger than t naught is what we defined it. It's just this is just the evolution operator in the position eigenbasis. And if you recall in one of the lectures, earlier lectures, we said that this time evolution operators solves the time-dependent Schrodinger equation this way. Good. So for t larger than t naught, this object solves the differential equation, which is just time-dependent Schrodinger equation. You guys recall this, right? This is what we first had and then derived the Schrodinger equation from this. So this is property number one. Property number two is if you take the limit of t going to t naught, it's basically calculating this bracket, x prime, x double. At t going to t naught, what you're calculating is this, right? Which is delta of, x minus x. Is this. Good? All right. If I'm in 3 dimensions, there's 3 here. So these are the two properties. Now, I'm going to ask you, so for t larger than t naught, to solve the Schrodinger equation. For at t going to t naught, you should take this form. At t less than t naught, what should it be? Zero. That's very crucial. Now, something funny happens. The solution is 0, and then until you reach t naught, and it has to become infinite at t naught. And then afterwards, it continues whatever it does. What do you do in these situations? It's discontinuous. In physics, mathematicians just like, well, okay, I shouldn't say anything. At this point, physicists just do the Dirac delta function, right? So you immediately learn that here is a Hamiltonian, here is minus I h bar dt. So the propagator solved this equation with an extra Dirac delta function in t, whose job is to match the solution when it was 0 before t naught to whatever it is afterwards. There's some discontinuity in the propagator, right? That's the job of this delta t going to t naught. The job of this guy is to make sure when t goes to t naught, you produce the right Dirac delta function. So the propagator solved this equation. Are there questions? Yeah.
Does the limit thing ensure that the paths stay within light mode?
Say it again.
Like, basically, we're saying the particle can't go too far in a short amount of time.
No, we're not saying that. There's which part make you think that?
As t goes to t naught.
As t goes to t naught, well, look at the expression. As t goes to t naught, this is my expression. T goes to t naught, this becomes 0. That becomes the identity, so x prime, x double prime. There is no light cone here. The only notion of causality that there is that things cannot propagate to the past. There's no maximum speed of light, any of that. As a matter of fact, if you try to put quantum mechanics in here, you're gonna relativity in here, you're gonna find a puzzle. This will be teaching QFT like first lectures. But good, yeah.
Is there anything when t goes to infinity? Like really, really far?
Anyone? Any thoughts?
Can you say like eventually it's gonna stop there?
So what is the behavior of this function in time? It oscillates. Could an oscillatory function have a limit? No. So you shouldn't expect that. That's very important. But we're going to see in a second, we're going to play a trick. As usual, we make things converge even if they don't. Good? Any other questions? surprised I'm in on time. All right. So what we're gonna do is we're gonna calculate the propagator. I'm gonna do this very quickly, and you're gonna work it out in detail in your homework or one of the maybe by yourself. I'm gonna solve this propagator. Find the propagator for you guys for a free particle. Right? So for a free particle, my Hamiltonian is just p squared over 2m, and the energy eigenkets are kit p's. All right. So what is the propagator? The propagator was, I should put it next to one of the expressions. Let me bring this back here. So here's the propagator. Let me put it here. So, oops. Here's my propagator. For a free particle, these are energy eigenkets labeled by p prime. Sum over energy eigenkets, because p prime is continuous, it's just an integral over p prime. And the rest is the same, where energy is just p prime squared over 2m. Good. So we're going to do this integral. What is this guy? We saw this before. It was e to the power of I p prime x double prime. What is this? This is just the same thing with x prime replaced by x double prime, complete conjugate of it, so it's minus sign. This is the extra term we added. This is the integral we have to do. Any questions about what I've done so far? These integrals come up a lot in physics. You cannot get away without learning Gaussian integrals. The way we solve them is by completing the square. So we complete the square. That's what I mean by saying that you should do this. And you find the following expression. It's just an exponent because it's a Gaussian integral. E to the power of I m over 2h bar t minus t naught x double prime minus x prime squared. And this is the exponent. You guys know what this integral is? So the core idea of the integral is this. Integral of p of x minus x, or y. This is the integral you have to. What does it look like? Anyone? Any guess? Sorry? Yeah, square root of pi over. That's something that depends on it. All right, and then this is what they've done. But you could look this up and do the integral. This is your propagator. Now, remember when I said for a free particle, the wave function in position space just expands. You could stare at this propagator and use it to interpret this wave function as the wave function spreading in time. Can you see it? Can you see that the wave function spreads in position eigenbasis as a function of time? Which property of this propagator tells you that? Sorry?
Like the variance of the exponential.
So the variance, yeah, okay. That's the phase part, right? So if you, this is, what is the propagator? Think about what the propagator is. The propagator is x double prime, e to the power of I h t minus t naught over h bar x prime. It's the amplitude to go from x prime to x double prime after this much time has passed. So what you would like to say is take the probability to go from x prime to x double prime and stare at the probability expression as a function of time, right? When you calculate the probability, the phase goes away. You are only left with that piece. And then you know this is proportional to 1 over square root of t minus t naught. As t grows, the wave function spreads wide. You guys think about that. But you might come up with your own way of thinking about this as well. All right. Any questions? I'm gonna make a bunch of comments, and I'm gonna try to move towards path integrals. We'll see. Yeah.
Are we looking at as a Gaussian
Yeah.
structure with the discrete line with expanding?
Yes. Yeah. So if you calculate the probability, yeah. Okay. Yes. Exactly. But as usual, a physicist writes an expression and stares at it for a while, right? That's you being physicist. You have to look at these expressions, calculate them. Part of your job is to calculate them, but then another part is just stare at them, try to interpret them. If you don't take the second step, you are more a mathematician. I should not say anything. Anyway, all right. I do work with mathematicians and I love working with them, so I should not. All right. Now, what I'm gonna make is a bunch of comments about the propagator. The propagator is an incredibly important object in physics. So what is it? Look at this. So all of these properties could be viewed as from this expression, right? So propagator is the is related to, is what it is the matrix elements in position eigenbasis of the time evolution operator. What happens if I look at the amplitude for the particle to not change its position? I get something, right? So this is a diagonal matrix element. What happens if I integrate over dx prime? Give me an interpretation of this.
Trace.
This is trace. This is trace of the time evolution operator. Right? Just I'm summing or integrating all the diagonals. What is it? Well, I think this is what the expression is in. I think I had a 3 here. Doesn't matter. I'm not very consistent. You know that, okay. All right, so let's calculate it. Well, I think we said that too. If you want to explicitly do this calculation, you take this expression, put x prime equal to x double prime. This looks like, let's just focus on this bit. So then this piece becomes sum over a prime, x prime, e of a prime squared. What is the sum? Interpreted in words. You have an energy eigenket. This is the probability of an energy eigenket to be in position x prime. Sorry, this is the probability. Maybe I should write it the other way around. That's easier. This is the probability of some ket x prime to be an energy eigenket a prime summed over all a prime. What is that? 1. Right? So that's just normalization of the wave function. That bit goes away. This bit goes away. And you're left with, oh, wait a second. Sorry about that. I think I did the other way around. I knew that first expression. So I'm going to do it this way. And I'm going to interpret this as, this is the probability for an eigenket a prime to be in position x prime integrated over x prime. That's 1. This bit is 1. So all I'm left with is sum over a prime, this face. That makes sense. Why? Well, trace, I can write it in my favorite basis. We said this basis independent. Let's write it in energy eigenket basis. You see out here? Do you see this? All right, what is that? That is sum over a prime. This is an energy eigenket, so it becomes sum over a prime, e of a prime, e of a prime, e to the power, oh god, to the power of I e of a prime t minus t not over h bar, and thus this is just 1. So we recover our expression. Now, if I replace t by it over h bar with beta, it becomes like a partition function. What I'm just telling you is a very, very deep statement. I leave it to you guys to think about it. There is a connection between quantum mechanics in d space dimensions and classical physics at finite temperature in d+1 dimensions. And the connection goes through that change of variables. In this connection, the Schrodinger equation becomes the heat equation. If you take the Schrodinger equation, make that change of variables, it becomes the heat equation. It's called the classical quantum correspondence. You go 1 dimension less, you higher, sorry, to make it classical. Good? It's just something for you guys to think about. Any thoughts? Questions? Yeah.
There's like the Minkowski transform. It's like
Minkowski said?
yeah, like you you change like time to ICT or something.
Oh, no, it's called, the terminology is called Euclidean, it's Wick rotation.
Yeah.
Wick, W-I-C-K, someone. It's basically this. It's basically this. There's a long story. I don't want to go on tangents. I'm more happy to tell you about it. If you continue in theoretical physics, a huge part of your career is going to be about this. Every time you do these connections, these things, doing this transformation, to mathematicians, they raise eyebrows, like they're suspicious. This is called analytic continuation, because right, that's what it is. You have a function of t, and you assume this function is a function of a complex variable t. Now, analytic continuation is not always allowed. There are some conditions. Mathematicians study all of this, and a lot of nonsense physics has been produced by some physicists who didn't know why. They were just naively doing analytic continuation. My supervisor, PhD supervisor, used to say that you have to apply to get a license for analytic continuation. All right. Enough tangents. All right. Next point is the following. So we defined this trace thing is a function of time, right? Let's Fourier transform it and write it in terms of frequency or energy. I want to interpret this. So this is another very, very deep statement. There's so much that could be extracted. There's so much you could extract from this object. All I've done is I'm taking g of t and I'm Fourier transform it as Fourier Laplace transform because I'm integrating from 0. Sorry. Minus I infinity. What is Laplace transform? What's the connection? Do you guys remember what Laplace transform is? What is it? Anyone? So you know what Fourier transform is? There's a t variable in there. Make this substitution of variables, it equal beta, you get the Laplace transform. Anyway, so you do this transformation. All right, let's do it. We said that this is just sum over a prime, e to minus I e a prime t over h bar. So it's multiplied by this. You bring the two together. This is an oscillatory function forever, and you want to integrate it over time. It doesn't converge. This integral doesn't converge. However, if you give this E a little bit of positive imaginary time, it will converge. I encourage you guys to do this calculation. And in the limit of epsilon going to 0, you recover this. All I'm saying is this expression that you might have used as physicists, not realizing what's the mathematics of it. Up to 2 pi's or something. Right? So this is the physics of that. What you obtain is that the Fourier transform trace of the time evolution operator is this function. As a function of E, energy eigenvalues appear as its poles where it blows up, right? So the knowledge of energy eigenvalues could be compactly represented as the knowledge of this function. The spectrum of this function knows about the energy eigenvalues. So this is just for you guys to know. I claim that this is a reformulation of quantum mechanics. Somebody hands you the propagator, you will have to be able to read off everything from it, including the energy eigenstates, energy eigenfunctions. I just told you how to read off the energy eigenvalues. Just calculate this object, look at its poles, and those are the energy eigenvalues. This is how we discover particles. We'll look at this function, we plot this function in experiments, and look where it shoots up, shows the divergence. Oh. All right. So apparently our time is up. Yeah, okay. All right. Any questions about this? So I didn't get to the path integrals, but the rest of the lecture you should read for yourself. It's building towards the path integral. But I'm gonna pause here and ask for questions. So summarize first and ask for questions. So what did we do today? We first went over the WKB again. We worked out 2 examples. One of them was just an infinite potential, well, with some arbitrary thing in the middle. This was classical region. The particle was classically allowed. We used WKB to solve it, and we saw like a simple quantization condition. The next example was a tunneling amplitude, right? We saw that the tunneling was controlled by the, we solved the equation on the left side, on the right side, these were phases, and to connect the two, there was an exponential decay that would connect the transition amplitude to the incoming wave. And that was the probability for my punch to make it through, even though it's classical fluid and I don't have enough energy. Then we switched gears and talked about the propagator. Propagator is nothing but the time evolution operator written in position eigenbasis. Physically, in words, if you want to interpret this, is the amplitude to go from position x prime at time t naught to position x double prime at time t. What we didn't get to is to discuss how you could turn this into a path over all, an integral over all path, and you could recover quantum mechanics using this method of path integrals. It's in the rest of the lectures, or it's in Sackler. All right, any questions? Yeah.
So kind of in the definition of the propagator, we used, I guess, a discrete spectrum for the energy eigenvalues, right? Now, if you take that, like a free particle, go to a continuous spectrum, is it just kind of the usual replace that summation over A prime with?
Yeah, okay. Yeah, because of integral. Yeah.
And then how does it relate to, I guess, this bottom one?
Oh wow! Beautiful, beautiful. So what if you have a continuous spectrum? It looks like there is just like continuity of poles. There's a long story associated with this. There's so much physics. A function, the poles could be continuous. The poles can meet and form branch cuts or branch points. There's a lot of physics into this. It goes into this. But for now, we're just talking about discrete spectrum. Yeah, there's like so much I can say about that. Very good question. You're in the right direction. Okay. Now let me just say a set of words. No, any questions? Let me not add extra stuff. All right. If there are no questions, let me just say one thing for those of you guys who do read the rest of the path interval. So the way classical physics comes out of it is beautiful. So you have to perform a path interval over all these paths. And each of these paths has an action associated with it, S. That was in the phase, right? What is the classical path? Do you have ideas? Least action. The principle of least action comes out of quantum mechanics. That's it. So in this formulation, Hamilton or whoever was that came up with the principle of least action, they were just mathematically driven, but this comes out of path intervals. All right, thank you so much, guys. It's actually not least action, it's extremum. It could be maximum action as well.